Sun. These monsters lie at the center of every large galaxy. Micro-black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. "12 billion years ago, the universe was littered with the remains of first-generation stars, and billions of second-generation stars were born from these clouds. Small groups of these new stars were drawn to each other gravitationally and merged to form ever larger and larger groups. Our own galaxy, the Milky Way, is an example of a spiral galaxy born in this early era. Today, it contains about 200 billion stars and is still growing as it absorbs small neighboring clusters of stars. The center of our galaxy is in the direction of the constellation Sagittarius. And like most large galaxies, there is a monstrous black hole at the center. The disk of our galaxy is about 100,000 light years across, and on average, 12,000 light years thick. Our own sun is a third-generation star, and is located about 2/3 of the way out on the spiral arm named Orion. We are about 26,000 light years from the center. The Milky Way is a member of a group of 20 or 30 galaxies and star clusters called our local group. The largest galaxy in this group is our sister spiral galaxy, Andromeda. Is it possible for distant galaxies to be moving away from us faster than the speed of light? And if it is, would it be possible for us to see them? Surprisingly, the answer to both questions is a resounding yes. How is that possible? How can something travel faster than the speed of light? Today we will try and paint an accurate picture of the universe based on the Lambda Cold Dark Matter model, which is the best cosmological model today. Once we have painted that picture, the answers to our questions will be straightforward. Let's assert that some kind of space-time quantum foam sort of something existed before our own universe began, before our Big Bang. Then we simply let Heisenberg's uncertainty principle go to work for us. If we look at the tiniest speck allowed by quantum mechanics, a small volume with a Planck length as its linear scale, the speck would have a volume of 10 to the minus 99 cubic centimeters. And the largest amount of mass or energy that we could put in this volume without it becoming its own black hole is about 1/100,000th of a gram. Interestingly, the uncertainty principle allows this much stuff to be created out of nothing for as long as 10 to the minus 43 seconds. Not a very long time, but it will prove to be enough. Because if that much energy is created in the form of a certain type of scalar field, then we have just successfully created a universe. The best model of how our early universe grew after that initial quantum fluctuation created it includes inflation, a period when the scalar field divides space into a brief period of extreme exponential expansion. During inflation, space erupted from its tiny beginnings into an unknowably huge volume. This enormous expansion generated an enormous amount of gravitational binding energy, at least 10 to the 85th grams. And this was counterbalanced by a corresponding group of positive energy in the scalar field. What began as a mere fraction of a gram of energy has now become 10 to the 85th grams. This is a huge number, large enough to account for all the matter and energy that exists today. But notice that the total energy in the universe is within a quantum fluctuation of equaling 0. As a byproduct of the enormous growth of space during the inflationary period, tiny quantum fluctuations grew into macroscopic fluctuations in the density of the scalar field, making it ever so slightly lumpy. This lumpiness